Welcome back to the first year course, Atomic Structure chapter. So after studying the Bohr's model, limitations of the Bohr's model and so many other concepts like the Heisenberg's uncertainty principle, etc. Now let us go for the quantum mechanical model. Quantum mechanical model. In this quantum mechanical model, the Schrodinger and various other scientists, they have considered both the particle nature as well as the wave nature of the electron, that is dual nature of the electron, and they have derived some expressions, and that expression is named as the Schrodinger wave equation. So we can write this as the Schrodinger wave equation as del square psi plus 8 pi square m divided by h square into E minus V psi is equal to 0. Here this del square can be replaced by as d square psi by dx square plus d square psi by dy square plus d square z by d square psi by dz square plus 8 pi square m divided by h square E minus V psi is equal to 0. So this del square or del is actually named as the Laplacian operator. Laplacian operator. Actually, this psi stands for the wave function. Psi is wave function. When we consider this wave function, the electron behaves like a wave, and it is actually revolving around the nucleus in 3 dimensions. It is x-axis, y-axis and z-axis can be considered as the 3 directions. So when you consider that wave function along the x-axis, y-axis and z-axis and take the double order or second order differentiation. So all these equations and expressions, explanations is not required for the 11th standard level or first PUC level, but still just for the information I am giving you this equation. That is called as the Schrodinger wave equation. In this equation, h is Planck's constant. That we know very well. M is mass of electron. Mass of electron. And E is the total energy. Total energy. This actually includes the potential energy as well as kinetic energy. And V is actually potential energy. Potential energy. When we consider this equation, that is a psi function, and it is having the second order differentiation, that's why we have to integrate and solve this one. What is important for us in the first PUC level is, the psi itself is not significant. So psi is actually wave function. But actually when we consider this as a wave function, and electron behaves like a wave as well as a matter or a particle. That's why the square of the wave function will give rise to the probability of finding the electron. Probability of finding an electron. This we call as orbital. When we find the solution for various x, y, z axis directions, then we get various values. So this psi square gives rise to probability of finding the electron, that is called as the orbital. But actually for first PUC level this is not required. But simply remember, this gives rise to the wave function nature of the electron. It is considered as the wave nature of the electron as well as particle nature because mass is included. When we solve this Schrodinger wave equation, we get various solutions. And three important solutions to find the probability of an electron in the atom is considered as the orbital, and these are defined by considering these quantum numbers. Quantum numbers. There are 4 quantum numbers that we consider in total to define the probability of an electron. So the first quantum number is principal quantum number. Principal quantum number, and this has been considered as the prime energy level as we consider that in the Bohr's model. The second one is the azimuthal quantum number. Azimuthal quantum number. It is also called as the subsidiary quantum number. Subsidiary quantum number. It is also considered as the orbital quantum number. This is indicated with L, and it has been proposed by the Sommerfeld. The third quantum number actually gives the orientation of the orbitals in the various electric and magnetic field. We know that each individual line in the hydrogen spectrum splits into the various number of spectral lines in presence of the electric and magnetic field. In presence of the electric field, it is called as the Stark effect. In presence of the magnetic field, it is called as the Zeeman effect. So those splitting can be explained by considering this magnetic quantum number, that is M. It is also considered as the orientation quantum number. Orientation quantum number. This has been explained by the scientist called Linde. And the fourth one, that we consider the spinning of the electron around the own axis, that is called as the spin quantum number. This is indicated with small s. So there are 4 quantum numbers: principal, azimuthal, magnetic and spin quantum number. There are some interrelationship among these 3 kinds: principal quantum number, azimuthal quantum number, magnetic quantum number, etc. So these 3 are derived from the Schrodinger wave equation. But as such, this spin quantum number is independent and it can have the values of plus half, S can have the values of plus half or minus half. So this can also be indicated with the upward arrow and downward arrow, indicating the spinning of the electron around its own axis. If it is indicated with the upward arrow, it is nothing but S is equal to plus half. If it is indicated with the downward arrow, it is S is equal to minus half. So these 4 quantum numbers, relationship among these 4 quantum numbers, we will study in the next video. Thank you.